So, welcome to this last lecture ever in my life. So if I'm a bit more carried away and emotional than usual, that's the reason. So don't worry if I start crying. That's just common thing, right? I'm gonna miss it, but I had a new job as of yesterday. So, but that's not the topic of today. I just wanted to share this with you. This is the topic of this last lecture for you. And the purpose now is to make you ready for the exam. And I will be there on the Sunday with you in my office, feeling with you and for you at the same time. So let's get you ready for that, to have you not having to sit here again next year with another teacher. So I'll spend the first 45, a little plus minutes on going through the entire course once again. And then we'll spend 5 minutes and one slide in going through the course once again. And then I think I will skip this part, actually. I looked at it and I'm going to pass it on to my colleagues. And as the new director, I will be looking into that people are following up on those comments, of course, which is part of my new job. I'm looking forward for that particular part of it, actually. Also that part. Then a little on the perspective, since this is only an introductory class. I think I've mentioned that a few times. There is a whole big bunch of courses and classes you could pursue if you want. Some of you should take a few. Some of you should take a lot. It's a good career move to make these days, to go for something related to data. And then we'll end up looking at the exam from last time, and I can have some questions. I will just share some thoughts about how you should proceed. And we can have a look at how it looks. You will have seen that already, I'm sure, because all your quizzes and throughout has been previous exam questions. So you've been practicing exam from day one in this course. So, to the overview. We had 12 lectures together, number 1 to 12. Here they come in the order, almost in the same order as the chapters and the contents of the lecture notes, with a little bit of fluctuation at the end. This is the order I gave the lectures to you that I put in here again. So let's, we could sort of split it here with the basics and the middle part. And then all the really interesting part, well, it's interesting, everything, of course, but these were the 3 splits we can make. Data's probability, 1 and 2 samples, that's the basic setting and where we teach you the statistical reasoning and thinking. And then sort of going on from there to more detailed modeling, regression type modeling, and then maybe a bit, this one could in fact conceptually have been part of the middle section, actually. But now it came at the end for all sorts of reasons that I'm not going to bore you with now. So let's move on and go to the beginning again. What did we do when we met each other here the first day? Well, I told you, and if you look at the first chapter, here the concept is, here is some data. Let's have a look at it. Right? That's data science, data analytics, business analytics, data mining, machine learning, whatever words are out there are about all this, learning from data, looking at data. Or maybe I should say, yeah, the first part is just, we started out by looking at data in elementary school. Some time back, 3rd grade or something, the first time we saw some data in an Excel sheet probably. And that's still an issue. Let's think about how to look at data in good ways. Let's think about summary statistics to tell the story about data, mean, standard deviations, quartiles. Summaries of location and summaries of variation. Two very basic principles in telling story about data. And simple graphics. This is not a graphics course, but it's clear when you go to this and when you leave this university and you go to Grundfos or Maersk or Danske Bank or Novo or where the heck you go to look at data, then of course graphics maintain to be very important. Data visualization is one of the 7 components of data science, which is the modern expression of what some of us have been doing for 25 years by now. But nevertheless, it's very good that the rest of the world finally woke up, and then there was a little bit of a digital revolution going on that helped the world to wake up also. But nevertheless, some of us worked with data science for 25, 30 years, actually. Some of us had a pretty good view on what was important for the future back in 1983 when I made my choice of which way to go in my life. Let's go for data science. I'm sure in 2017 that's going to be a pretty important and hot topic. So, good choice. We still need, this is where you can be creative, right? I didn't teach you a lot here, or almost nothing. We talked about the box plots, scatter plots, histograms, cumulative histograms, things like that. Bar charts, I didn't really teach you. This was something we knew in advance. But remember to use those things still. These things, the graphics, can be used as explorative tools to just look at the data, and they can be used. And I have to admit, we didn't have time to dig into that to a strong degree in this course. They can be used at the end of the modeling procedure, where you're gonna convey the story about what the modeling actually helped you to find out about the real life phenomenon. There you should and could and should use graphical tools also to display the model output and not only data exploration, actually. We gave you some hints about this, but this was not a general data science course. This was a statistics course. And data science is much more than that, of course. But also statistics. Then, the specifics of this course is the inferential statistical thinking. Classical statistical reasoning, almost the language or philosophy of science as it has been developing over the last hundreds of years, is what this course is about. To do this, we need probability tools and probability theory. That is the language of uncertainty, or the language of formalizing what we don't know. Everything we don't know, we put into the language of probability. If you're a really hardcore thinker and into physics, you might challenge me on that, what we should really call random, and what's something you could explain by certain deterministic models in case you knew the model and you were complete in control of the system. That's quite a discussion that could keep you awake for a few beers a Friday night. So go ahead and do that. Invite me for a beer. No, don't do that, actually. Anyway, everything we don't know or we are uncertain about, we use the language and the procedures and models of probability to be in control of that, to the degree that we can be in control. We started out by the discrete distributions. Definition of a random stochastic variable, density function and distribution function. The density is the individual probabilities, right? And the distribution function is the accumulated probabilities. We can define mean and variance. We can define mean and variance for any discrete, for now, probability system or model out there. That's pretty neat. We can actually, if we can put a phenomenon that we are facing, the control of the energy system in a house or whatever, if we sort of can define the randomness of the system by discrete measures here, we can also start extracting expectations to this system in terms of means and variability by those theoretical constructs of mean and variance. And then we met 3 specific guys within this neighborhood, from this neighborhood: the binomial, the hypergeometric and the Poisson distributions. There are hundreds and hundreds more out there. You met 3 of them. These are pretty much used. The binomial most of us would have met in some way or the other. That's clearly the coin tossing binary outcome random model. So that's pretty used a lot. And we can deal with those probability models. Probability theory, I emphasized that when we did it, is a very important field and topic of mathematics and has its rights of its own in an engineering context also. Everything related to risks or queuing models or whatever. There's a lot of hardcore math and probability stuff that can be really important, also in finance and you name it, where the mathematics of probability theory is very important also for many engineers. It comes up in all sorts of areas. For our course here, all those stuff, really nice. You would have to learn that in other courses. We have probability courses, stochastic process courses, random stochastic simulation courses, and you name it. For us here in this course, we give you the absolutely minimum of probability reasoning thinking to make us able to do some stats. And to make us able to do stats from an engineering perspective, meaning that we do not prove all the theorems and all the things we do. If you want proofs of statistical theorems, you should have been at another university. Because if you go to stats courses at KU Mathematics, you get all those proofs. Well, we give you some proofs whenever we think it's worthwhile to be able to know it. This is a how university, not a why university. And I'm sure that's why you're here. So that's good. Why is okay. Nothing wrong with why, especially when it brings something on the how account also. But nevertheless, we are quite happy with the why guys at the university. I come from there myself. But it's much more fun to work together with the how guys out here. So that's really nice. We need the concept of probability both in the discrete context as in a continuous context. It's the same in these two chapters, or these two sections, sorry, in the same chapter is kind of parallel, right? We need to be able to talk about probability systems for something that by nature is quantitative and continuous, like measurements of alcohol in the blood. I don't know why I came to think of that after last Friday, but nevertheless, we can have density functions, distribution functions, now defined on a continuous scale. So instead of summing up things when we need to do accumulation, we have to integrate things, right? And we have this little thing that might confuse us sometimes, that compared to the discrete world, where density means the probability of specific events, the probability of a 0 or the probability of a 1, then density in the continuous world doesn't really mean anything meaningful, apart from probability by x, by scale or something, and that's an odd name, so we call it a density. So it's kind of how dense the probabilities are, and they can only be interpreted as probabilities when we start integrating them over non-zero areas, right? If you just have a point under the density curve, I mean the area of a point under the curve, that's 0, that doesn't have any interpretation, and the density itself is a bit difficult to interpret. The density can have very large values way beyond 1 if it's distributed on a very narrow interval, right? So it's just to say densities themselves are a bit awkward to think of, but probabilities are meaningful. That's the little difference between the discrete and the continuous world. Usually it doesn't really, challenge us a lot in the daily work with stats. This is not the daily challenge that we're faced with. It's just in the understanding of everything, that's a little thing. We can define mean and variance generally for continuous probability systems. Pretty neat again. There are some mathematical definitions of means and variances that really are integrals if you're into math from a mathematical analysis point of view. Means and variances are integrals. And then We could have some rules for those. These were these mean and variance rules, especially the variance rule were pretty important for us actually. The variance of a sum is the sum of the variances, which means that the variance of a mean is the individual or joint variance divided by the n. This is this divided by n that makes us able to do statistical inference. The information grows as n, the precision grows as n grows, right? The more observations, the more precision we have. That's in a way the essence of it. We met normal distribution, log normal, uniform, exponential. The normal had its own little role there because, yeah, we saw that later, it has a special role to play for us. We use all these basic probability to do the basic stats. And here I wanted to make a little cut.